What challenges real-world engine thermal efficiency? Have you ever wondered why engines can't convert all the fuel's energy into useful work? Let's break down the challenges that real-world engine thermal efficiency faces. Thermal efficiency is the ratio of useful work output to the total energy input from fuel. While the ideal Carnot cycle shows the maximum theoretical efficiency, practical engines often fall short due to several factors. First, let's talk about thermodynamic limitations. The Carnot cycle represents the highest possible efficiency for a heat engine working between two temperatures. However, it requires all processes to be perfectly reversible and infinitely slow. This means zero power output, which is not practical for engines that need to deliver power quickly. Real engines must find a balance between efficiency and power output, which naturally reduces thermal efficiency. Next, we have irreversibilities and losses. Real engines deal with issues like friction, turbulence, and non-ideal combustion. These factors lead to energy being wasted as heat instead of being converted into useful work. For instance, mechanical friction in moving parts and pumping losses, which are the energy used to move air and fuel through the engine, can significantly lower efficiency. At low speeds, gasoline engines can experience losses due to throttling, which restricts airflow and increases the work needed to pump. Heat losses are another major challenge. A large portion of the energy from fuel is lost as heat through engine components like cylinder walls, exhaust gases, and cooling systems. This heat does not contribute to mechanical work, further lowering overall efficiency. Material and temperature constraints also play a role. Increasing the temperature difference between the hot and cold reservoirs can improve efficiency according to thermodynamics. However, engine materials limit the maximum operating temperature to prevent damage. This restriction keeps real engines from reaching the ideal Carnot efficiency. The design of the cycle and the properties of the working fluids can affect efficiency too. For example, raising the compression ratio in internal combustion engines can improve efficiency, but it is limited by fuel characteristics and the risk of engine knocking. Alternative cycles, like Atkinson or Miller cycles, can offer better efficiency, but they may come with trade-offs in power density or complexity. Emission and environmental regulations are also important to consider. Efforts to cut down on pollutants often requiring engines to operate in ways that can reduce thermal efficiency. For example, exhaust gas recirculation lowers combustion temperatures to reduce nitrogen oxide emissions, but this can also decrease efficiency. Lastly, practical engineering trade-offs come into play. Enhancements like turbocharging or supercharging can improve overall power and global efficiency, but they do not necessarily increase the intrinsic thermal efficiency of the engine cycle itself. In real-world terms, modern internal combustion engines typically achieve thermal efficiencies around 40%, with some advanced designs reaching up to 50% under specific conditions. These improvements result from careful cycle adaptation, combustion control, and waste heat recovery systems. Understanding these challenges clarifies why real engines cannot reach the ideal thermodynamic limits. Ongoing research continues to focus on balancing power output, emissions, durability, and efficiency within these constraints.